Okay, friends. So in our previous class, what we have seen is how to develop the interpolating functions. Um, we have seen that the Newton's linear interpolation functions, then Newton's quadratic interpolation functions. We have also solved couple of examples which will help us in determining the intermediate values of the function from the known values of the data points, or the function which is passing through these data points, which also helps us in evaluating the interpolating function. So in this class, what we have to understand, another alternative for for developing the interpolating function, that is called as Lagrange approximation. Now, see, interpolation means is to estimate a missing value of the function by taking a weighted average of the known function's values at the neighboring points. So for example, if this is the curve, these two are the data points, I want to determine the intermediate values, and this is passing through these two data points, this function. So basically the weighted average of these known values fx1 and fx2. So suppose we have the linear interpolation, which is actually uses the line segment, you know uh, as in the case of Newton's interpolating functions. We have seen that line passing through two data points, and we have also seen that from similar triangle, or from you know the slope, comparing the equal slopes, we are able to obtain the slope passing through two data points, let's say x0 y0 and x1 y1. So for these, the slope will be y1 minus y0, x1 minus x0. And from the point slope equation, we can determine, the function's intermediate value. This is your point slope equation, and this can be rearranged. I mean, we will substitute the slope value here. So we will be able to obtain, and slightly rearrangement of the equation will give us actually the Newton's linear interpolation function. But this will also help us in determining, how the Lagrange interpolation function can be evaluated. So if I rearrange little bit of this function, I can get y is equal to y0 plus y1 minus y0, x minus x0 divided by x1 minus x0. Now, if you look at the, when we want to evaluation this function, of course, at x0 and x1, it produces y0 and y1. So I can call, okay, if it is a polynomial function, Newton's polynomial linear interpolation function, it gives you p of x1 here, y1 minus y0. This is 0. I have used this equation for evaluating the function at x0 and x1. And so I have to substitute, instead of x, I have to substitute x0 in one of the equation. So this gives me y0 in one of the cases. Second, it gives me, this is 1, it gives me y1. So Lagrange interpolation function was discovered by French mathematician named Joseph Louis Lagrange. He used actually the same equation of Newton's interpolating function, but slightly in a different version. Okay, so slightly different version to find out the polynomial. We will see how we can determine that. He noticed that if we could write the same equation, the similar equation, in a slightly different form, and then we will be able to see that we are getting the weighing function, which will be multiplied with the function's value, and slightly different form of interpolating function will be able to. So we will see how to determine that Lagrange version of interpolating function using the linear interpolation function given in the form of Newton's interpolation function. So this was our original equation of the first order linear interpolation. So we have to slightly expand this function y0 plus y1. I am separating out this term x1 minus x0 minus y0 x minus x0 x1 minus x0. So we will bring these y0 terms this side. So we will be able to, and also we multiplied this denominator factor, we will get y0 x1 minus y0 x0 minus y0 x plus y0 x0 divided by x1 x0, and of course this side remain as it is, that is y1 x minus x0 x1 minus x0. So we try to simplify this, that this term is going to be cancelled. We will be writing the terms which are going to be cancelled. These positive negative terms will be 0, and we will take out y0 on left side common, and we'll be able to see. And of course we change the sign because denominator we are going to write in the form of x0 minus x1. Okay, so we can interchange the sign of this, that is x minus x1. In the denominator it will be x0 minus x1 plus y1, this term remains as it is, x minus x0 x1 minus x0. So see, the idea behind this is, you see here we have written same equation in a different form, and you will be able to see that this is function's value evaluated at fx0. This is nothing but y0, and this is the function's value evaluated at fx1, which gives you y1. And these are the Lagrange interpolating coefficients 1, L1, and this is the second Lagrange interpolating function, that's L2, and of course both are function of x. So what we write is, if you evaluate, you will be able to see that suppose I want to determine the function's value at x 0. If I evaluate the first function's value at x0, L1 x is equal to, so we write it separately, x0 minus x1. Now we try to evaluate this at x equal to x0. So at x equal to x0, what we get is x0 minus x1, and this remain as it is. It gives me 1. And if I try to evaluate this same function at x equal to x1, because we are having only 2 points, x0 and x1. Sorry, this is fx0, fx1, x0, x1. So if we evaluate the same Lagrange interpolating coefficients at x equal to, same equation, if we evaluate x equal to x1, it gives me 0. And similarly, if you try to see the second interpolating Lagrange interpolating coefficients, that is L2 x equal to x minus x0, x1 minus x0. So this, if I evaluate at x0, it gives me 0 value, and when I evaluate this at x1, it gives me unit value. So this kind of property is definitely going to help us that the Lagrange interpolating coefficients gives us unit value at first point and 0 value at the other point. So the nature of that is, it is going to give me that graphical interpretation of that. This function is L1 x, which is x minus x1, x0 minus x. If this is x0 and this is x1, and second interpolating coefficient gives me, here this is L2 x, and this is nothing but x minus x0, x1 minus x0, provided these are x0, x0. It gives me unit value at x equal to x1 and 0 value at the other nodes. And this is very important property, this is called as Chronicle delta property. Now we have seen that we are going to get y0 and L1x, y1 and then L2x, and L1 and L2 are actually nothing but those are the weighing coefficients. And graphical interpretation of this is, and I'm slightly writing the same formula in a slightly different version, that is fx L1 f of x1 plus L2 f of x2. This is nothing, instead of x0, x1, I am calling now x1, x2. Slightly different version, and you know that L1 is equal to x minus x2, x1 minus x2, L2 is equal to x minus x1, x2 minus x1. So as I told you, L1 and L2 are the weighing coefficients, and of course if you try to see the graphical interpretation of this, if we want to plot the curve, this will be something like, because these weighing coefficients are actually, when you multiply it with functions known value, it is going to help me in determining the intermediate value. But the graphical interpretation of the first term, this is L1, this is the functions, and this is the second one. So first is the value of this is f of x1, but the entire behavior of this will be L1 times f of x1. So weighing coefficients are multiplied with f of x1, and here weighing coefficients are multiplied with L2 f of x2, and then it is going to give us the actual behavior of these terms. And again, this is a value of function fx. Similarly, the second order Lagrange interpolating polynomial can also be written, and we will also learn the technique, a simple technique, which is, because what we have talked is about linear interpolating coefficient, but we will also be writing and trying to see that how you can, with the simple technique, how you can evaluate for the other cases. So second order, I mean, you can follow the same strategy because it has to follow, as I told you, the chronicle. Sorry. Delta property. This is very important because Lagrange interpolation function has to follow the Chronicle delta property. Meaning of this is it has to give you unit value of that at the first node and 0 at every other node. So suppose if we talk about quadratic, then there will be L1, L2, L3. So it should give unit value. These functions weighing coefficients of Lagrange interpolating coefficient should give you unit value at, let's say there are 3 nodes x1, x2, x3. Unit value at x equal to x1 and 0 value at the other nodes. So if you evaluate L1 at x1, it should give you unit value. If you evaluate L2 at x2, it should give you 0 value. If you evaluate L3 at if you evaluate not this, if you evaluate L1 at x2 and x3, it should give you 0 value. So L1, L2 at x2, L3 at x3. Sorry, x2, L1. Basically, it should give you the function L1 should give you unit value at first node. L1 should give you 0 at the other nodes. Similarly, suppose I talk about L2 function, it should give you unit value at that particular corresponding node or joint or distance x equal to x2. It should give you a unit value. L3 at L2 at x3 should give you 0 value. And the last one, L3 x1, L3 x2, L3 x3. So this should give you one value, and other nodes it should give you 0 values. And this is called as property of Chronicle delta property. So we use this simple property which will help us in determining whether it is linear, quadratic, and even the higher order Lagrange interpolating functions. So for the for the second order Lagrange interpolation function, of course, the total summation will actually give you, when f of, let's say, f1 x L1, f1 x1 L1 then f of x2 L2 plus f of x3 L3. So second order Lagrange polynomial can be written like, you can write here like this: x minus x2, x minus x3, x1 minus x2, x1 minus x3, f of x1. Sorry, here there shouldn't be nothing, plus x minus x1, x minus x3, x2 minus x1, x2 minus x3, f of x2. And the third quantity will be x minus x1, x minus x2, x3 minus x1, x3 minus x2, f of x. See, if you see this L1, L2 and L3 and try to evaluate that, L1, L2, L3 at 3 different points, you will be able to see that these equations, this entire function follows this Chronicle delta property. Now we will try to see that how you can actually construct, this kind of coefficients. So we will write a general form of, the function as L1x, let's say x minus a, x minus b and c. We will write in a general, let us name it L of x. Okay, now ABC of course are constants, and it has to satisfy the Chronicle delta property. So we want this L to be vanished. Let's say we want to develop it for the quadratic, okay, and we want this function to be vanished at, if there are 3 points, we want this function to be vanished at x2 and x3. So we can achieve this only by introducing a is equal to x2 and b is equal to, because then only if I evaluate L of, when I'm writing the, of course I want to write the first, so L1x, the function weighing coefficient at first node. Okay, so x1, x2, x. Of course, this is going to give you parabola, but if we want to evaluate this, it should give me 0 values at the other nodes, x2 and x3. So this can be written only by when you substitute a equal to x2 and b equal to x3. So, nominator portion is done here. If I write this, and if I evaluate this function at x2 and x3, it is going to give me 0. L1, the first one, L1x, out of 3 functions, 3 different quadratic interpolating functions. So now the remaining thing is this C. So how we can evaluate this C? It again has to meet the conditions. When you want to make L1 of x equal to 1 at x equal to x1. So if we evaluate x equal to x1, and bring this term in the denominator, then nominator denominator will get cancelled and it is going to give me 1 unit value. So can we write denominator as x1 minus x2, x1 minus x3 in the denominator, because we want now L1 of x equal to 1 at x equal to x1. And this can be achieved only because the nominator is being done by, it should vanish at the other two nodes x equal to x2 and x equal to x3. So nominator side is being done when we write, instead of a and b we will write x2 and x3. It is going to give me L1 function at x2 and x3 as 0. And that first condition of the Chronicle Delta property is being achieved here. Okay. And then second condition is, instead of C, what should we write? Instead of C, what should we write? It should, this condition is still satisfied for the remaining, that is L1 of x equal to 1. So this can be achieved if we evaluate the denominator side at x equal to x1, then it is possible, and bring that term in the denominator. So what we have done, x equal to x1, x equal to x1 here, and we have written it in the denominator, and the denominator side will be as it is. So this has helped us in evaluating at least the first of the coefficient. Now similar approach we will follow for the second strategy also. Second, to evaluate in the second coefficient. So it is, now you can see here, like instead of now x, we want L2x should be, I would say, it should give you unit value at node 2 and 0 at the other nodes. So of course we can write something like, x2. The first should be x minus x1 and x minus x3 in the denominator. And second is easily evaluated, like evaluate that with x equal to x2 minus with the nominator side. So x minus x1, x minus x3, x2 minus x1, x2 minus x3. So if you want to evaluate this function at x1 and x3, it should vanish. So first term is already clear in the denominator, and denominator, when you evaluate the same nominator side at x equal to x2, it should give me one value, unit value, and that's how the L2 can be written. Now the third coefficient, how we are going to write? It is very easy now that we want to vanish, at node 1 and 2. So I simply write x minus x1, x minus x2, and I will write that at x3. So x3 minus x1 and x3 minus x2. And same procedure can be followed for even the cubic function. So that I am leaving it up to you for the exercise purpose, that you have to derive the cubic Lagrange interpolating function. Now coming back to our example which we have solved in the case of last time for the linear interpolation function using Newton's interpolating formula. So what we had to derive is, now we may consider maybe the example, let's say we have the second order linear interpolation function. So let us see, 3 data points are given, x1 equal to 0, x2 equal to 20, x equal to 40, and function's value will give you, let's say 3 point, this is known values given f of x3. These are the given values, and if we use a formula for interpolating function, that is fx1, the linear interpolation, x minus x2, x1 minus x2, f of x1 plus x minus x1, x2 minus x1, f of x2. So if I will be using these first two, data points to evaluate now x equal to 15. I want to evaluate the function's value at x equal to 15, which is not given here. So I will, if I use a linear interpolation, I'll be using first two values, and here I'll be using first two values. So this is of course Lagrange linear interpolation formula. So I'll write at 15 what is the value of function. So x1 is 0 minus x2 is 20. Function's value is 3.85 plus 15 minus 0, 20 minus 0, multiply by 0.8. So this is going to give me 1.5. This is just a matter of substituting into the formula. Then we evaluate the linear, the quadratic, that is f2x. The formula for quadratic just now we have derived. So we have three data points. We will be using all three for the use of quadratic. So I am writing the direct values. It is x minus x2, x minus x3 divided by x1 minus x2, x1 minus x3. So 15, 0 minus 20, 0 minus 40, multiply by 3.85. Two more terms. The above formula which we have written for the quadratic, that same formula you have to use. Sorry, 20 minus 0, 20 minus 40 into 0.8, 0, 0, plus the last term, 15 minus 0 into 15 minus 20, 40 minus 0, 40 minus 20, multiply by 0.212. And this is going to give you 1.3316875. So you can evaluate basically the, using Lagrange's interpolating function. It is the efficient way of determining the function's intermediate value.